The most recognizable ball in sports is an object of surprising geometric complexity that usually goes unnoticed. The classic ball you see on the pitch is not actually a true sphere. It is a complex polygon pretending to be round. Looking closely at this Telstar ball, you see the flat shapes making up its structure, specifically the black pentagons and white hexagons. Geometers call this specific arrangement a truncated icosahedron. This specific configuration is the most efficient way to force stiff, flat panels of leather into the shape of a functional, high-performance globe. If you want to stitch flat panels tightly together without leaving any holes, the logical approach is to choose shapes that nest together perfectly. Nature already figured out how to do this perfectly. Bees use a continuous grid of hexagons to build their honeycomb entirely without empty space. Let's look at the math inside this diagram of a single hexagon. If you measure one of its interior angles, it comes out to exactly 120 degrees. When you slide 3 of these hexagons together so they meet at a single corner, those 3 angles add up perfectly to 360 degrees. Because that joint balances to a perfect 360, the surface stays completely flat. You can add 1,000,000 more hexagons, and you will remain on a flat plane. You can never build a ball this way. To break out of that perfectly flat trap and force the surface to curve, you need a structural disruption. Look at this comparison. While the hexagon sits at 120 degrees, a regular pentagon has an interior angle of exactly 108. Swapping one hexagon for a pentagon on our flat grid shifts the central joint's math. Adding 120, 120, and 108 gives us 348 degrees. We are suddenly left with a 12-degree empty gap. When you sew these physical pieces together, you force those outer edges to close that space. That missing 12 degrees is what forces the flat material to buckle, cup upward, and eventually close into a tight sphere. You might wonder if a brand put exactly 12 pentagons on the ball for style, or if there is a deeper physical reason. The answer lies in this equation, Euler's formula for polyhedra. It serves as the mathematical blueprint governing any closed three-dimensional shape. A classic soccer ball has 32 total faces, 90 edges, and 60 vertices. Plug those into Euler's formula, 60 minus 90 plus 32, and it perfectly balances to 2. When mathematicians isolate the variables for a shape where 3 faces meet at every corner, they find a rigid rule. You can use infinite hexagons, but to successfully close the sphere, you must use exactly 12 pentagons. The iconic look of the ball is an inescapable result of universal geometry. This geometric rule extends far beyond sports. It was leveraged extensively by architect R. Buckminster Fuller. Fuller used this exact mathematical pattern to design geodesic domes. By distributing physical stress across these interlocking polygon panels, he built massive structures that were incredibly strong, yet surprisingly light. Inside Fuller's own home, you can see how those flat pentagon and hexagon joints seamlessly curve the high ceiling over the living room. The math allowing a ball to roll across a pitch is identical to the math letting humans build towering architectural pavilions without a single internal support column. We can zoom out to enormous buildings, but we can also zoom way in, down to the level of carbon atoms. Look at this diagram. Chemists discovered a highly stable carbon molecule comprised of exactly 60 atoms, structured as a microscopic cage with the exact same geometric layout. The recognizable shape led scientists to name the molecule Buckminster fullerene, or buckyballs, honoring the architect. A microscopic molecular cage, a vast geodesic dome, and the struggle for the ball at the World Cup all share the exact same mathematical skeleton. A player lining up a shot is driving a foundational law of physics and geometry straight into the net.